So, hi everyone, I'm Ettinger. I've been using Dafny' to teach a course on formal languages and automata theory, and I'd like to tell you some of my experiences with this course. So, a traditional way of teaching automata theory would be on paper. It's a mathematical effort. It's quite abstract. And when you have bugs in your machines, the designed machines, you will maybe find it when you hand in as a student, your assignment and get the feedback some days later, or maybe even slower. And how do you debug your, even when you realize that there is an error, how do you debug your machine? It could be like a programming effort, right? You could think of this as maybe running your machine, if it would be executable, debugging it, and hopefully also verifying correctness of your machines, of your automata. And this is what I was trying to do with Dafny', and let me share some experiences with that. A little bit about my personal journey with formal methods. It started for my doctoral studies at Oxford, doing program transformations, so refactoring transformations, designing or deriving algorithms with calculational proofs, however, on paper only. And then I've been teaching 3 different courses using Dafny' since 2014 in academia. The main one was programming with proofs, and starting with Carol Morgan's book, and then a little bit of Rustan's book. And then that was in an elective course. Then I was asking myself, can I use it in required courses? I did one course on logic and set theory that I presented 2 years ago in London in the Dafny' workshop. And then this automata theory and formal languages course. And just to say that this was, I was teaching this 3 times. The last 2 of those in Ramat Gan Academic College in Israel were for students that already studied ahead of that logic and set theory with me in Dafny'. So they already knew Dafny', so that made things easier for me on this semester for those 2 times. These days I'm working at NVIDIA doing formal verification for C, combinations of model checking and deductive verification for C, C++, and some Ada and Spark. So my course followed strictly the Elaine Rich, the textbook by Elaine Rich. And in this particular talk, I will show you deterministic finite state machines. However, I've formalized a good portion of the course with Dafny' to different levels, so I will show. But let's focus on DFSMs, deterministic finite state machines. So this is from the textbook. So a DFSM, it has states, it has a starting state, it has accepting states, it has a transition function or relation. If it's non-deterministic, this is deterministic, and it has an alphabet. Right? In Dafny', it will look like this. I have here, we have tuples, so I have a quintuple here of sets of states, alphabet, the transition function, and the starting state, and the set of accepting states. For simplicity of this, I had getters with the names from the book, like K, sigma, delta, little s, and a. And then let's make it into a programming course. So, so let's have, for example, a visualizer. This is something I added after the course, but hopefully for the future. A visualizer, I added that with a kind of a vibe code. It's a visualizer. You can run your machine. You can debug it. Question is, how do you write your machine? So there could be, I could imagine a tool that will help you write the machine. But so far, it's been textually in Dafny, writing the machine. But when I was teaching this course, I gave them a simulator, like in the textbook, DFSM Simulate, that takes a machine and the string, an input string, and prints out those configuration, like in a main method. And what's in this simulator, I'd like to show you a little bit. How the simulator is written and how is what's here. This is the machine. So here we have the machine itself. I have a function for the transition function. It would be a relation for a non-deterministic machine. And there is the machine itself, this quintuple. And sorry. So yeah, so what is a formal language? It's an infinite set of strings. What is a string? It's a sequence of characters, or symbols. What is a symbol? It's a character, built-in character from Dafny. So Dafny really helps me. I have some functions about operations on languages. And then here's our language in the textbook, a language for this particular exercise of finding numbers with odd number of ones in them. This is the way with I-set, infinite set comprehension, that it could be written in Dafny. And the textbook had a simulator for the DFSM that was imperative. So I did the same. So here's the DFSM simulate. It takes a machine and a string. It returns a Boolean of whether the string is in the language accepted by that machine. So why is there spaces here? Because I turned it also into to print out the. So it's like a simulator, not only a. So it prints out the states of the machine, but there's more space for the spec, saying, well, so accepted should be true if and only if W, the input string, is in the language of the machine. And what does it mean to be in the language of the machine? I formalized it like in the book. And Dafny allowed me to do all that. So that was really nice. Let me quickly go through some definitions to see what do we have here, and ask ourselves, what do the students gain from that, and what does the teacher gain from that? So let's see. For the precondition, we needed to say what is a valid string, that all its characters are from the alphabet, and what is a valid DFSM, that it doesn't jump, the transitions function does not jump to an unknown state. It should all be correct, and it should be, the function should be total in the states and the alphabet. And then, so this is the language of a machine. It's all strings that are valid and are accepted by the machine. And this is again from the textbook, just transliterated into Dafny with yielding, what state is yielded by the machine for a certain string. You don't have to read all that now, but and for the post condition, what do we have here? Another function that is the semantics of the machine. It's written in Dafny, and then we are back to the simulator. Now it's a fully verified simulator. Because we know what it means to be the language accepted by a machine, we can add some loop invariants that track the saying really that the suffix that is remaining will end in an accepting state if and only if the original string was from the language of that machine. So that was nice. And that was like a bonus, the verification of this imperative simulator. What the students gained from this approach is now they can write their own machines and prove correctness. Prove that the machine is really accepting the expected language. A lemma that ensures that the language of the machine they are writing for this example from chapter 5 of the book, example number 4, is the language expected. We have the language, we have the machine, we want to prove. And let's just go through a proof and ask ourselves what's in there. We don't need to understand the proof, but what's in a proof like that? There's a base case for an empty string. There's a non-empty string. There's some calc here that is calling, that is invoking another lemma for each state. There is a lemma for each state, and it kind of tracks the transition function in a way. So it's five. Thanks. So it's a proof by induction with some calculations, with some mutual induction. Like here we see on the calc that we are calling lemma 5,4 for Q naught, for Q0, right, for the first step. And here, in case we see a 1, there is a calling the lemma for itself, so it's recursive, and so on. So the structure of the proof is really, it imitates the structure of the machine. And then students can write their own homework assignments. They can debug them with the simulator. They can, for bonus points, try to prove correctness. So in summary, for the deterministic finite state machines, what we know now how to do, since we defined formally the semantics of a machine, of the language accepted by a machine, we now have a fully proved interpreter, and the students can write their own proofs of their own machines. So in a way, the theory comes alive. That's the goal of this. So what's more from beyond this in the course? Just a regular second year formal languages and the automata theory course. There's non-deterministic finite state machines, similarly formulated, fully formulated. And then there are parts that are partially formulated, that you have a simulator, but not everything is provable. Like, for example, I love this, the pumping lemma for regular languages. So how can you prove a language is not regular with contradiction, leading to contradiction? There's context-free grammars that will generate all strings possible until a depth of some derivation, some pushdown automata, some Turing machines, really beautiful. Only deterministic Turing machines, because otherwise it would be harder. And some of those tools, again, I've been using the textual simulator, and there is also the web one that I generated recently. And potentially then, one could come up with a test suite and either provide it to the students that they will test the work for themselves, or be a teaching assistant in grading eventually. Because if you give it to the students, well, maybe they will do trial and error and not understand really why everything was correct. There are stuff in the course that I didn't do in Dafny at all, decidability questions, parsers, and other algorithms that I did like in the textbook, because that was too much. But if I had more years to teach, that could be great. Finally, the takeaways. It's a way to turn an abstract mathematical course into a concrete programming-like course. It's possible to really fully prove correctness of some things if the definitions are there, and the students are learning by doing. So thanks very much.